In this video, we're going to be talking a little bit more about reactions. A lot of our reactions are not one way. They are actually going to be reversible reactions. So reversible reaction is one in which the conversion of reactants to products and the opposite, the conversion of products to reactants, is occurring simultaneously. This will be shown by a double arrow in the equation. So if you've seen an arrow going one towards the forward, so one towards the products, and one towards the reactants, that is a reversible reaction. And whenever we have reversible reactions, we tend to reach a chemical equilibrium. This will occur when the rates of the forward and reverse reaction are equal. So the rates or the amounts will end up flatlining overall. Now, even though those reaction rates are the same, the concentrations do not have to be the same on both sides of the equation. So whenever we're dealing with these, we will end up looking at the equilibrium position. So looking at the relative concentrations of the reactants and products at equilibrium. So often we have one side of the reaction that is favored. So it'll indicate whether the reactants or products are favored in the reversible reaction. So which one is going to have more at equilibrium, the reactants or products? And if this keeps going and one part of the reaction runs out, the reaction will stop. Sometimes you will see this denoted by the length of those double arrows. So here in the first one, if you have a double arrow and the longer one is pointing towards the products, that means that that forward reaction is producing more products. So the products would be favored in that situation. Look at the second one where the longer arrow is pointing towards the reactants. That would indicate that the reactants are favored at equilibrium. And oftentimes we can reach a dynamic equilibrium where the reaction rates and the concentrations are the same. And a lot of times those will be shown as equal sized double arrows. We're going to go over equilibrium constants tomorrow, which is another way that you can figure out which side of the reaction is favored at equilibrium. Today we're going to include Le Chatelier's principle. This is looking at what happens if you adjust a reversible reaction. So if you increase or decrease something within the reaction. So when we're at equilibrium, there is a balance that exists within a system because those forward and reverse reaction rates are the same. Any change to the reaction can disrupt that balance, and the system has to adjust in order to restore that equilibrium. So it will shift the overall equilibrium either towards the products or towards the reactants. So Le Chatelier's principle states if a stress is applied to a system at equilibrium, the system will change in a way to relieve the stress. We're going to look at some of these stresses and how they will actually adjust the equilibrium of the system. Our first change we're going to look at is if there's a change in concentration. And all of this is a balancing act. So I know there's a lot of rules listed here, but one way to look at it is say that we have one of the really like old-time gold scales where it has the little fulcrum up at the top, there's two chains hanging down, and they have plates at the end of these chains. You may have seen this a lot of times. This is used as a symbol for lawyers' offices and stuff like that because it's a balance. Now think of if you add something to one of those plates, that plate will now be heavier and it will end up being lower than the other plate. So in order to rebalance them, you now have to add something on the opposite plate. So one way to look at this is if there's a change in concentration of a product or reaction, it will shift the overall equilibrium. So if you increase the amount of reactant, so if you add something to the plate on the left, the plate on the right will raise up, and in order to reestablish equilibrium, you need to make more products and add something to that plate on the right so that they will balance out. So there was an overall shift towards the products to produce more products. If you decrease the amount of reactant, if you take something off of that plate on the left, now that plate is too light. So you will need to add something onto that same plate that you removed something from, so on the reactant plate, in order to reestablish equilibrium. So the equilibrium will have to shift towards the reactants to balance out. And the same is true if you do it on the product side. So the general rule is if you add something to one side, equilibrium will now shift to the opposite side to reestablish equilibrium. If you take away something from one side, equilibrium needs to shift towards that side to reestablish equilibrium. So here we have a reaction. We have carbonic acid producing carbon dioxide and water. So say that I increase, let me change my pen color again. If we increase our carbonic acid, so the general rule was that if we increase, we need to shift towards the opposite side. Since carbonic acid is on our reactant side, our equilibrium will shift towards the right to make more products, to reestablish equilibrium. Same thing's true if I decrease carbon dioxide. This was the other rule. Let me scroll down a little bit so you can see. Now, carbon dioxide's on the product side. If I take away carbon dioxide, in order to reestablish equilibrium, I need to produce more carbon dioxide. So this will also be a shift towards the right. So the general rule is if you add something, it shifts towards the opposite side. So this was originally on our reactant side. If you take away something, it will need to shift towards that same side of whatever we took away. Since carbon dioxide is a product here, it will shift towards the product side. This same trend is true if our stress is a change in temperature. So an increase in temperature will cause equilibrium to shift in the direction that absorbs heat. If heat is the side where heat is not listed in the reaction. A decrease in temperature will cause equilibrium to shift in the direction where heat is released, where heat is actually listed in the reaction. So yet again, this is the same trend. If you add something, it will shift towards the opposite side. If you reduce heat or take away something, it will shift towards that same side. So one thing to note is that heat will always be listed in your reaction, or it will tell you if the reaction is endothermic or exothermic. Endothermic reactions will have heat as a reactant. Exothermic reactions have heat as a product. So here, if we were to increase the temperature, because temperature is on our product side, the reaction has to shift towards the opposite side. So this will actually shift left towards our reactant side. If we decrease temperature or cool down our system, we have to shift towards the side with heat listed. So this will shift towards the products and produce more products. If we were to do this with an endothermic reaction with heat on the opposite side, these arrows would be reversed. So you want to make sure to pay attention to which side of the reaction is heat listed whenever it gives you the equation. Another change we're going to look at is if there's a change of pressure or volume. These kind of go together. So remember, pressure and volume are opposites of one another. A change in pressure or change in volume is only going to affect the equilibrium of gases when there's an unequal number of moles of gas on the reactant side and product side. So this one is not a general trend that you can remember. This is the only rule that is slightly different. So we are going to need to count up moles of gas on our reactant side and product side. If there's an increase in pressure, equilibrium will shift to the side equation that has less moles of gas. So higher pressure favors less moles of gas. If we decrease the pressure, it will shift to the side of the reaction that has more moles of gas. So lower pressure likes more moles of gas. Remember, volume is the opposite. So if we have a high pressure, it's a low volume. So those are going to be paired together. If it's a low pressure, we're going to have a higher volume. So those will be paired together. So looking at our reaction, I'm going to list out our number of moles. So on our reactant side, we have nitrogen, 3 hydrogens. So that's a total of 4 moles on that side. Whereas on our product side, we just have 2 moles of ammonia. So if we have a higher pressure, it's going to favor the product side because there's less moles. If we have a lower pressure, it will favor the reactant side with more moles of gas. So this will be different based off of each individual reaction and the number of moles listed. That should be our last slide for the day. It is. Go ahead and practice using Le Chatelier's assignment that's posted in Canvas and think about all of these individual rules as you go through the steps.